Hello everybody, my name is Sunil Subedi. I am currently doing my PhD at STSU. Today I am going to present on the topic partition dynamic modeling of inverter with grid support functions. So with the advancement in the power electronics technology and the grid standards, the traditional converters are being supplemented with new IEEE standards 1547 advanced grid support functions. So with standard and the advanced control algorithm, the dynamic behavior of the converters varies significantly, resulting more nonlinear and the complex dynamics, which cannot be neglected. So due to the complexity and the scale of the power system analysis, researchers rely on the computational tools and the simulation to explore and understand the new phenomena from the integration. But there exists some challenges as the proprietary models changes in their parameters and the topology. And also, with the number of inverters increases, the conventional modeling techniques become imprecise and computationally intractable. So there is a need of general and scalable dynamic simulation framework that speeds up the simulation and make it computationally efficient within an acceptable accuracy. So we have proposed the linearized partition modeling up. So the figure here shows the piecewise characteristic of the volt-var mode defined by IEEE 1547-2018. So if we try to represent the whole model or the modes of operation volt-var or the volt-watt with a single linear model, then it do not capture all the detailed dynamics of the converter more accurately. The proposed flow diagram for the proposed work is present on the bottom. So we want to utilize the partition modeling where the set point, the V1, V2, V3 representing the different regions are further divided into smaller regions or the ranges, and then we want to utilize those ranges to represent the transfer function. We have used the square wave as a probing signal perturbing the voltage and the output current, and then is measured. Then we have utilized the system identification approach to identify the transfer function for different poles and zeros that minimize the cost function as least square error. The base transfer function representing each smaller range is selected based on the goodness of the fit and the complexity of the model, with the matrices normalized routine square error, percentage fit. So overall dynamics of the switching converter is captured by aggregating the transfer function during the course of simulation. So this process is repeated for each range of voltage magnitude, and all transfer functions are selected. So in order to test and validate the proposed approach in the electric scenario, we have considered the JIP load and model and the induction motor load to add further dynamic in the load profile. So we have considered two bus system based on the radial distribution benchmark. So we have also considered the detailed control current voltage source inverter, which is set shows that we study the volt-var mode in the detail despite other voltage sources are available. So with the general load profile is generated, then we compare the response from the detailed inverter and the aggregated linearized transfer function in the analysis part. So we saw that the terminal voltage changes according to the load profile, and also there is a sharp drop in the voltage at every instant of induction motor is turned on. It is because the induction motor demands the higher current while starting and the voltage drop down. So accordingly, the reactive power is also absorbed from the system and the voltage is reduced from the system. The bottom figure here shows the developed linear model closely follows the response from the detailed inverter model, where the reactive power is absorbed according to the system condition. So with the least square error of just 1.91%, we can say that it is closely following the detailed inverter model. Also, we found that the simulation is speed up by 4-fold compared to the detailed mode single run. So in conclusion, we can say that the transfer function model is faster, computationally accurate, and computationally tractable. It allows the utilities and researchers to perform the voltage dynamic study with larger number of converters. Since we have not considered the frequency dynamics in this case, we want to model that in the future. We'd like to acknowledge the National Science Foundation, Department of Energy, and the South Dakota State University Joint Research for supporting this research and providing the funding. Thank you.